Good morning and welcome to another edition of Ganashot Tech. In this edition or this episode, we are going to talk how we are going to use AI in a multimodal form in a multi-domain environment, right? Uh, to do this, episode, I have with me Vidya Raj Nema. Welcome to the Ghana Shot Vite. It's a great thing to have a young guy who's interested in AI on Ghana Shot.
Thank you so much, and good morning, sir. Good morning to audience, and Jai Hind and Jai Bharat. Thank you for inviting me.
Yeah. Before I get into the whole thing, let me first introduce Videy. Videy is doing his master's in the University of Alberta in computer science, and he's tremendously interested in AI. Okay. So that's his background thing. And we've been sharing thoughts on AI and how to use it in the armed forces. Right. As you all know, uh, today is a world of multi domain operations. And in multi domain operation, information is power. Getting information on hand is power. But having information in these times when there's an overload of information is a waste. So, how do you handle it? That's the first question. It's a volume of information which is flowing into us. We don't have the traditional methods of analyzing this information and converting into intelligence is just flooded out, right? So, you might end up in a situation where you have the information, but you don't know where to pick it up and how to analyze it. The second thing, information is flowing in from various sources, a multitude of sources. It's coming from satellites, it's coming as visual images, it's coming from radars, it's coming from all kinds of electronic emissions. So there's an electronic form, there's a visual form, and then there are a whole lot of reports in language form which comes in. So you're looking at a something what we today talk of a generative AI or large language models. The other two are probably discriminatory and in vision based computing. But the thing is, all these inputs come in different formats, and all this data has to be fused. And so today we're going to talk about data fusion through AI in a multimodal format in multi-domain operations. Sounds quite complicated, but Vidya will try and make it a little more simple and make you understand what we are attempting. Yeah, Vidya, all yours. Just give your thoughts and then we'll take it on.
Yes, sir. Thank you, and that's a really great introduction to this. Yeah, we'll talk about data fusion, and why we want to do it is obviously because of the domain awareness. And domain awareness is, in simple terms, it means having some operational knowledge of a particular, you're concerned about a particular maybe a field or a particular like area of influence, and you want to understand the interactions with maybe other domains also. So a domain can be something like land, sea, air, or now like it's also space, and you have cyber, you have electromagnetic spectrum, so whole lot of things. So you want to remain aware, and this is key to multi-domain operations. And yeah, and as you know, like multiple times we have like it's been talked about on this channel that the best technology is not necessarily the latest one; it's the one that helps you win, right? So domain awareness also helps in keeping it helps you to build technologies that are suited to your particular maybe terrain, adversaries, your modus operandi, your economy, your scientific expertise, ethics, and so on. So that's why it's quite useful, and data fusion is a key for it. And data fusion is refers to this integration process. So as sir mentioned, that the data comes from multiple channels which are heterogeneous. So you can have satellite or UAV imagery. You can have reports which may be in the form of language, or they may be in the form of speech, which is like raw speech signals, and you'll have to extract language out of it. Or it may be in other forms, for example, LiDAR or like haptics or acoustics. So a lot of different forms. So how to make sense out of it, and a simple strategy is just to have one model for each of these channels, but that's quite inefficient, because there's no like fusion happening, and there may be also conflicts between two or more channels. So a better strategy is to somehow do this data fusion, and in the realm of AI and machine learning, these channels are referred to as modalities. So a modality is how something is perceived. There's a whole field of multimodal machine learning, and like techniques from that multimodal machine learning can be used to do this fusion. Yes, sir.
Yeah. So, what Vidya is saying, he's made a very important point. Why you need fusion? He's actually answered the question. Why do you need fusion? You could get data and information through multiple channels, multiple forms, and you could process them separately, and you'll get three different pictures. But unless you put these pictures together, you don't get the real picture, actual picture. And to get an intelligent picture, you need AI. You need to process it because the volumes are still high, and especially with the language inputs which you keep getting, whose volumes are tremendous, right? So you need something different. On the other hand, things like processing, satellite imagery or imaging thing, that's a specialty on its own, right? And it doesn't easily fuse. That is why there's different modes of inputs which are coming to use some method through machine language to come to a common picture is important. Yeah, how do you go about it? How do you do all this? You could explain it to people in as simple terms as you can.
Yeah. Before that, just to add another point about domain awareness and data fusion, is that this domain awareness is obviously used to gather knowledge. It's used to make predictions in the future. It could also use for generative purposes, to like maybe like summarize some information. Like you have a whole lot of text and you want to summarize some information. But the interesting thing here is that in the predictions, these predictions can the variety of these predictions can be huge. So they can range from some quick predictions about some quick and immediate information about some imminent future, which happens, for example, at a tactical level, uh, to some long term planning strategies, to lay out, for example, policies at a strategic level. So the spectrum is huge, and accordingly the methods. Now, like from here we go to, as sir mentioned, that how can we do it. The methods also, like what we want to use it for, what we want to predict, that will have an effect on what methods are. So in simple terms, these in multimodal machine learning, all of this builds on three basic principles: that the modalities are heterogeneous, they are interconnected, which means they are connected plus they also interact with each other. All of these three principles form the basis of a multimodal machine learning, and we assume that there can be like four or five or any number of modalities, and we want to either learn some sort of representation or predict something or maybe generate a new modality. And a very recent example of a multimodal machine learning model is in fact this product released by Google called Gemini. It was recently released, so that's a multimodal model that has images, text, and stuff like that. So, in the basic terms, how this data fusion via multimodal ML, how this works, is that what it does in the first step is basically, uh, so suppose for this talk, what I will do is I'll assume that just there are two modalities, but it can be extended to others also, and those two modalities are like vision and language. So in vision, you divide the whole, for example, image into particular parts. So, for example, an image is can be classified as a list of objects. and a sentence or a paragraph or a essay can be said as a list of words, right? So the first step is to learn how the individual elements of the two modalities interact with each other. So, for example, some part of the of my satellite imagery, how it interacts with some piece of text from my language. And inside this, there comes a lot of different techniques where we could do fusion, where we basically are trying to learn a common representation of this. We could do coordination, where we keep the number of representations same, but we share the information, or we can do fission. Now, fission is very interesting because a lot of times two elements of across these two modalities may interact in more than one ways. So in fission, what happens is that even if you have two modalities, you can the fission can be into three or four or multiple of them. So the first step is basic, where you are just interested in the individual components across the two modalities. Now, in the second step, what you do is you expand this to the multiple components. So you take all the objects in an image and all the words. So, for example, like if you have, for example, an image of a say like a cricketer with a bat and helmet and stuff like that. So you will have bounding boxes that this is a bat, this is a helmet, this is a pad, this is a something like that, and then you will have correspondingly words in a language model. So the second step is to align objects in the image to the words in the sentence or phrases in the sentence. So that's the second step of alignment, and these two together, representation and alignment, together form something called contextualized representations, which are like the bread and butter of of every like multimodal framework. And these two steps act somewhat as a pre-processing to the further process. The third step is of reasoning. It's called something called reasoning, and reasoning is just very much similar to what people have like forward pass in a neural network. It can be much more complex. In very simple terms, it can be just a very simple linear neural network, like a with linear layers and like a feed forward neural network, and then you can just pass information. And in reasoning, what you are trying to do is basically you have multiple inference steps, and you exploit the multimodal alignment and problem structure. There are also ways, because we may want to have uh, everything interpretable, because in some safety related domains we may want to keep everything interpretable. So there are also methods by which the intermediate steps of reasoning they can be made human interpretable. Now this interpretability can range from like simple mathematical numbers to actually words telling that what each and every layer is doing. So that's the third part, where we combine the knowledge through multiple inferential steps. And after this, it sort of expands into three categories. One is obviously simple prediction, where you, for example, want to predict like it can be binary prediction, it can be a multi-class prediction, where you want to predict like you have 10 classes and you want to predict any one of those. So it could be something like a prediction, it could be regression, it could also be generation, where what you're trying to do is generate something. Now this is explored a little less, but it can be done. Like there could be interesting ways of applying this multimodal stuff in generation, and what it can do is it can help in suppose you have two modalities, you fuse them, and then you produce a third modality, which is like an emergence of a third modality. So this is something like you didn't expect that to happen, but the machine somehow figured it out, and then it is giving you some information. So
Yeah.
that's
Okay.
yeah.
Yeah, that's the outline which you're given.
Mhm.
I would suggest if you could show some representation figuratively to explain what
Mhm.
you're this thing, and then we could probably get a better understanding of what you have spoken.
So yeah, so modality. So what is a modality? So what we talked about the channels. So these are the modalities. So modality refers to a way in which something is expressed or perceived. It can be something like a language, audio, acoustics, video, speech, haptics. So haptics is very interesting because it's related to touch. And these modalities, they vary from raw modalities, which are very close to sensor. So for example, you will not extract language from sensor, you will extract a speech signal from a sensor, right? Similarly, you will not extract like object categories from a sensor, you will extract a raw image. So you will have raw modalities, and on the other end you have very abstract modalities, which, for example, speech, you can convert that into language, and then language you can convert into sentiments. And multimodal is basically, like, a simple definition is, yeah, obviously with multiple modalities, but a research oriented definition is that it's made of three principles. Uh, it's a scientific study of heterogeneous and interconnected data, where interconnected is a combination of connected and interacting. And what this means is, heterogeneous in very simple terms is, yeah, that the modalities have diverse qualities. So here modalities are represented with, like, a triangle and a circle. And these could be anything like vision or language. Heterogeneous means that they are different. So, language and vision are different and something like that, but they are different, but they have a common structure. If they were completely distinct from each other, then there was no point of fusing. They have some common structure, which is why you have these connections, shared connections, and these shared connections could be, for example, because of some correspondence. So, for example, you see rain and clouds together. So you know that, for example, there's some correspondence between rain and clouds, right? Similarly, sometimes you see some dependencies. So, for example, you had an image of a base, and you had a satellite taking periodically image of a base, and then you saw that something changed, and then there is some other modality, speed signal, coming, which is explaining that how what that change occurs. So there's a dependency of that speed signal towards that change in the satellite image. And we have interactions, obviously, and interactions occur when we actually do something with the modalities. So either we are trying to predict something, we are trying to fuse and generate a new representation, or we are trying to actually come up with a new modality. So that's where interactions come in. And multimodal machine learning, yeah, is basically this whole umbrella, which is a study of the computer algorithms that learn and improve using and experiencing data from these multiple modalities. So multimodal ML, you can have anything which is like supervised or self-supervised or reinforcement learning, and you can do the downstream tasks of representation fusion or modality generation or prediction. And like Gemini is from Google is a recent example of this. And all of this has six components, and these six components will help us better understand data fusion. So I'll go over them. Representation, the first component is a basic component, which is where actually the fusion steps in first. What it means is that you try to learn. Representation is basically the way a thing is represented. So, for example, an image can be represented via like a neural network layers. Like a word can be represented as a vector, right? So that's representations. And the first step, what it does is that it takes individual elements of the two modalities, and it finds the cross-modal interactions between them. So, for example, you have some object in an image and some phrase in a language, like a passage. You try to find the cross-modal interactions between them, and you can do it via fusion, where you are trying to fuse the data, reduce the number of representation. You can. There are also techniques of coordination where you like share the information and keep same number of representations, or you can have fission, where and this is very interesting because there can be more than one ways the modalities interact with each other. So in fission you basically are expanding your representation. The second step is something called alignment. Now, since you have now the first step helped us find the local representations. Now from local you are going to global, because so previously we considered, like, only one element in each of the modalities. Now we are considering all the elements, and alignment means finding the connections between elements of modality A and modality B. So for example, in this figure we have this like a player, and there are bounding boxes that this identifying that this is a hockey stick, this is a helmet, this is a ball. So we align these bounding boxes to, for example, the phrases in a sentence. So now you are no more local. You consider all the data that you have, and there are again like a lot of sub challenges inside it. And the main thing is contextualized representation, which is basically the combination of these two steps. So you're learning the local representations plus you're learning the connections. So this caters to both the interactions and the connections part. Now, these two components act as pre-processing. After this pre-processing is done, you have something called reasoning, where you have multiple stages of understanding and inference. So these could be, in very simple terms, these could be, something like a feed-forward neural network. In more complex term, it could be something like a transformer. So, but nevertheless, it's something like, you pass it through many, many layers of understanding. It has a lot of trainable weights, and we can have there are techniques to have intermediate stages as interpretable also. So this is the third step. And after the third step, there are various things that you can do. You can predict something, which you may like want to do a lot of times. So for example, there are 10 classes and you want to predict which out of these 10 is the most probable. You can also do generation, and this is very interesting, because what we will want to do is emerge or generate a new type of modality, which we have not seen previously. So that comes into creation. You can also do summarization, because if you have like tons of data, and you want to create a compact summarized representation, then summarization helps a lot. So there are techniques of summarization, and overall this generative process is like reverse engineering. So basically reverse engineering the previous three steps, so that you can generate new things. And in generation, there are a lot of, for example, ChatGPT is a generative model. There are generative models in images also, where you just pass in a sentence what to generate, and it will generate it. So, and then the fifth component is something called transference, which is very interesting, because a lot of times, our data will come from real world, like objects. So for example, satellites or UAVs, and a lot of times there are like noises and disturbances associated with it. They can be due to environmental factors, or it may be due to inherent error in the instrument. So a lot of times one of our modalities may be like poor in quality, it may be prone to disturbances. So what we can have is some other modalities which are available during training. They can help transfer the knowledge to it and help it enrich. So this really helps, if we have a primary modality which is noisy and have disturbances. And the final step is quantification. Quantification is simple. It's basically, you develop theoretical and empirical frameworks around how to do multimodal machine learning. That's just quantification. So yeah, this is the overarching like pipeline of how, for example, any multimodal machine learning algorithm will be built, and any multimodal machine learning algorithm can be used for our data fusion purposes.
Yeah, I
Right, sir?
think yeah, I think you outlined very well as to how AI can be used uh, to get to what we want in a multi-domain process with multimodal inputs. Right. Now, uh, for many people, this might have gone over the top, but for many people, it would have triggered a line of thought.
Hmm.
What we have today put across is got value in its own way. But for many people, or in fact, for most people, what they have to understand is there's a way forward. That AI can be used in multi-domain operations with multiple inputs to fuse it and get a logical output out. So how do you think this can all be put together in your visualization? And you give me your thoughts on how do we go about doing all this now in
Hmm.
the real world?
Um, so I think in the real world, firstly, what we'll have to do is whatever I presented actually, that's suitable for like a student working in a lab getting clean data, like which is like without any like distortions, and data available in huge quantities, like millions of images or millions of articles to train on. That's appropriate for it. Firstly, what we will need to do in real world is have a lot of pre-processing, because what we may have is, for example, you want an image of a base. We may want to have it from different angles, because like we may want to have
Yeah.
it in day, afternoon, night. So, and because the amount of data will be less, we may want to actually look into methods that work in low data regimes, because these big transformer models, they are very suitable only in large data regimes. So firstly, that will be the pre-processing step, and we'll have to do that individually for each of the modalities. And then after
Okay.
that, I think the way forward will be to explore a lot of fusion methods. And from what I from like the works that I have seen till now, there are like, I think 50 or 100 of hundreds of fusion methods, ranging from very simple, like simple additive fusion where you're just adding things, to extremely complex. So what we should do is start from the very simple ones and keep on moving from to complex ones. And another thing that we would like to do is that if we want to fuse two modalities which are very close to the sensor, right? So they'll be raw modalities. Now, a type of algorithm required for an image is very different from the type of algorithm required for language, right? So in that case, we may not be able to fuse it. So we need to actually think of algorithms that can be common. So like masking is an algorithm very popular. It's used in like GPT training and all. It's also used in vision, which is actually common to both vision and language. So that's why it can be used as a bridge and do it. So if you can find like other algorithms also to do that, that will be helpful as well.
Yeah. So that means you say let's say we want to just uh, fuse vision based inputs and language based inputs. So first you have to process the vision based input separately based on the kind of volumes you'll get there, and then you have to you know develop or rather process the language based inputs to a level, and then you start getting them together and use techniques to fuse them. Am I right?
Yeah. Yes, sir. Yes, sir.
Right. And you have to generate volume. I mean, like you said, base.
Mhm.
When you see a base, the characteristics of a base are generally uh, fundamentally the same. It'll have a security
Mhm.
fence. It'll have a place where you park vehicles. I'm giving you in a very simplistic form. It'll have
Right,
a
sir.
place where you have generators, power outputs, all that. That's the same, but each base will differ from the other. It'll have an
Mhm.
approach road. Okay, so these characteristics are the same, but each base will be different. So if you think, okay, I can process it with just three images or four images of one base, obviously you will not get a thing. But
Mhm.
just think of it. You are trying to now process the case for about 100 bases which are across the border. So
Mhm.
that means now you generated volume. You 100 bases, satellite images over say 10-15 days, just giving you a
Mhm.
representation to idea,
Mhm.
and each base being photographed say twice or thrice in a day. So that means just for one base you'll get about, over 15 days you'll get about 45 to 50 images. Now you
Mhm.
multiply it over 100, then you're getting about 500 to 5,000 images. Now doesn't that become a volume data which you can then start processing with some, like what you said, with common inputs and differentiated inputs,
Mhm. I
right?
think it really. Yes, sir.
Yeah, yeah. Go
Yeah.
ahead.
So I think it really depends on. So for example, if we have like 5,000, for example, it really depends on the capacity of our model, because in machine learning, actually, there's a very basic, like when I started learning, all of this stuff, back like a couple of years ago. So there's a basic thing called overfitting. What it means is that if the capacity of a model is large, which means the number of weights that you want to learn, if they are large, and the data is like the amount of data that you have small, then what will happen is that your model will perform very very well on the training data that you have, but it will most probably in a lot of cases fail to generalize. So what it means
Right.
is that it has adapted so much to that small amount of data that it is not generalizing better, right? So there are a lot of ways to mitigate this, and one simple way is over like having more data. So
Yeah,
uh,
but
I
what I've been trying to put across to you is this, just to give you an idea as to, if you're looking at it only with one base, you will not have much data. But you expand the whole horizon, you get more data. And then the
Yeah.
more data you get, the better your models get trained to
Mhm.
analyze them. And then, of
Yeah.
course,
Yeah.
you also have some data logic, language inputs on this basis. So once
Mhm.
you get those language inputs on this basis, then you can fuse them and then you get the volume. Then I think the issues which you are highlighting would get mitigated to a large extent, isn't it?
Yes, sir. For sure that they can. And another interesting point that you mentioned is that we are getting data not just from images, we are getting data also from like language,
From
even though they may
languages.
be different on the like on the front they may be different, but underlying characteristics that they have, they are the same if we go to abstract level
The
because
same.
it's related to that
Yeah.
same base, right? So it can
Same.
use
Yeah.
that. Another thing that can be used is some pre-training. So lot of these, so for example, GPT, I think the full form is generative pre-training, something like that. I don't remember.
Yeah.
But pre-training is like nowadays everyone uses like for example
I
in
think it is
industry use
I
pre-training.
think it's generative pre-training technology.
Tra- no, I think it's Transformers. I think actually,
Okay,
I
whatever
think
it is.
yeah, yeah. Actually when the first GPT paper came out, actually it was just like another research paper. No one like I'm not like people cared about it, but it wasn't like this will become so huge. So actually, no one really checks the full form. But what I'm trying to say is that a lot of so for example, if you want to do, I'll give a simple example. If you want to do sentimental analysis, that's a very simple task. Single model, right? That you have been given a paragraph and you want to identify that whether the person like whether what's written there is it like in anger, is it like happy, is it sad or something like that, right? So uh, uh, basically what happens is GPT is made of this something called transformer, right? And transformer itself is made up of an encoder and decoder. You take decoders, you stack a lot of those, and you get GPT. And you take decoder and you stack a lot of those, you get GPT. And you take encoder and stack a lot of those, you get something called BERT, which is used in Google search and all. Now this BERT, what happens is this what they have is that they have pre-trained models. That means the model is pre-trained on a huge amount of data which is already available, for example, open source on internet, which is not necessarily for sentimental analysis, but it has a lot of knowledge. It's like a repository of knowledge, and then what you do is just add a simple linear layer over that thing and then just fine tune it for your sentimental analysis. So you need less amount of data plus you are getting those pre-trained knowledge. So I think we can do similarly pre-training here.
Yeah, we can. So that means AI has tremendous use in this business of data fusion,
Mhm.
multi-domain operations. Only thing we have to start somewhere, right? And I think the way forward in this, personally, I feel after having listened to you is that we have to just get into it. Right.
Yeah,
Your final thought
definitely.
before we close on this complicated process, which you've tried to simplify. It might sound, like I said earlier, it might sound a little complicated for many people, and for many people, it might start making sense. And that's the way I look at it. Your final thoughts, Vijay.
Yeah. So yeah, you like you actually said like you're spot on in saying that we actually need to get our hands dirty with it because this is something which is very general and we are inevitably headed towards this like algorithm like or like information or AI revolution, right? Looks like for example like we had industrial revolution and then we had like what two world wars, right? So similarly, like the world is like we have to catch up with the world, and we need convergence to keep track of technology. Developing globally competent systems, right? And I think this domain awareness, with the help of this data fusion stuff, is actually very critical step in that pipeline. What it will help in is that, like for example, it can help in like predicting courses like enemy course of action. It can preemptively queue like the ISR, like intelligence surveillance and all, at some like areas of interest to confirm or deny certain actions. You know, um, and yeah, there are like tremendous scope of predictive as well as generative. But one thing that so actually two things that I would like to conclude with is that obviously there needs to be an ethical code and ethical regulation around this, how people will use it. But more importantly, there must be humans in the loop. You cannot just
Yeah.
you cannot just like close your eyes and then just hand it over everything. There should be humans in the loop, and in fact, like my research area, like right now, is something called human in the loop reinforcement learning, where we study this. So human in the loop must be paired with these AI systems to review and assess the, like the veracity of the model, because what I like to say is the objective must be to build the machines that are compatible with the humans and not necessarily indistinguishable, right? So we
Yeah,
want to
I think
make it compatible. So
yeah, I think
yeah,
you
yeah.
I think you made your point. I think you made two very important points. One which you started with. The best technology is not the latest technology. It's that
Mhm.
technology which wins you the war. And the second thing is no matter how much AI progresses and no matter how much you get into this AI revolution, the human in the loop is the most important guy. And he's
Yeah.
the chap who's going to decide finally how to handle this business of AI. Right. I think we've made a lot of progress in understanding AI for multi domain awareness and where it is going. Right. With this, I'd like to thank you, Viday. Have a good time in Alberta. Go ahead. We'll have more interactions on this. Thank you and good evening.
Thank you, sir. Thank you. Good evening, and thank you to the audience, and Jai Hind.